we want to go on to section 4.3. 4.3 is about graphing rational functions. Graphing rational functions. So we've already done some analysis of rational functions, like finding vertical asymptotes, horizontal asymptotes, x-intercepts and y-intercepts. I want to continue our analysis and then be able to graph these. There's a lot of complexity in graphing them, so we're kind of building things up. So the first big result here that we're going to introduce is about rational function behavior for x-intercepts and for vertical asymptotes. So how does the graph of a rational function behave at the x-intercepts and the vertical asymptotes? That's what we want to find out. So let's say you have a rational function. We're going to call it r of x. And on top, it has a factor of x minus c here, right, of multiplicity n, and then times another polynomial. Then on bottom, it has a factor of x minus a of multiplicity m, and then another polynomial. Now, this is a rational function that's been reduced. So anything in common between the top and the bottom has been canceled out. So the first thing we want to focus on is the x-intercepts. What happens at the x-intercept? So when this n here is even, n is the multiplicity of x minus c. When that is an even, then the graph kisses at x equals c. When n is odd, then the graph crosses at x equals c. Okay, so let's just kind of see what's going on here. So here I have my kind of generic rational function with x minus c, a factor, on top of multiplicity n. So if I'm finding the x-intercepts, I would take my factor here of x minus c. I set that equal to 0. And I get x equals c. So I have an x-intercept that's c. Now, if this is even, if n is even, so if n even, then graph kisses at x equals c. So an example of that, okay, so we have c here, let's say. So your graph would do maybe something like this at c. Or maybe your graph would do something like this at c. One of those two things is going to be going on, okay? So the other possibility is if n, our multiplicity, were odd. If n odd, then the graph crosses at x equals c. So drawing a graph here, I have c. So I have an x-intercept here at c. So either my graph can go across there in an increasing direction, or it could be maybe in a decreasing direction like that. One of those two things is going to happen. It's going to go across. Okay, so that's basically the characterization for x-intercepts. I mean, it's just exactly like with polynomials. There's no difference with the polynomials. Now, with rational functions, we often have what are called vertical asymptotes. Vertical asymptotes. So when you look on the bottom, where you have the factor x minus a and a multiplicity of m, if m, the multiplicity of the bottom factor, if that is even, then the graph goes in the same direction on opposing sides of the vertical asymptote x equals a. And if the multiplicity of that bottom factor x minus a is odd, then the graph goes in opposite directions on opposing sides of the vertical asymptote x equals a. So let me give you some idea about this. So thinking about vertical asymptotes, to focus on vertical asymptotes, I'm going to look at my bottom factor here and the multiplicity m. So basically I'm going to take x minus a, set it equal to 0, and now I'm going to get x equals a as the vertical asymptote. So this is not a place that hits the x-axis necessarily. It's not a point on the x-axis. It's a line, it's a vertical line that your graph will approach but doesn't ever touch. So what happens if m, the multiplicity of that, is even? Then the graph has same behavior. I should say goes in the same direction. And same direction about the vertical asymptote, x equals a. So let me draw a picture of that, the same direction. So the idea is we have this thing called a vertical asymptote right here. Okay? And your graph is going to approach that on one side. So let's say coming from the right side towards the vertical asymptote, our graph goes up. Well, if it goes in the same direction about x equals a, then on the left side it has to go up as well. So this means the same. They're both going up. Both going up. On opposing sides. Right? That's what that on opposing sides of x equals a. Or you could possibly have something like this. Let me draw another situation that could be valid. So here I have my vertical asymptote here at a, right? And your graph is going to approach there from one side. Let's say from the right it goes down forever towards a. And that would mean on the left side it would have to go down forever as well because we have the same direction. So when m is even, when the multiplicity is even, then they both go in the same direction, either both up or both down. Okay, what happens if the multiplicity is odd? Then the graph goes in opposite directions. About the vertical asymptote. Or you can say on opposing sides of the vertical asymptote. That's actually the way I wrote it in the statement. On opposing sides of the vertical asymptote. Okay, so let me draw pictures of that. So if you have an odd multiplicity for your factor there in the denominator, you're going to have opposite directional behavior about the vertical asymptote. So here's our vertical asymptote right here, a. And let's say on the coming from the right side, it goes up. That means on the left side, it would have to be going in the opposite direction, going down towards a. Or another situation that's valid could be like this. Here's your vertical asymptote a. And let's say coming from the right towards the vertical asymptote, your graph is heading in a downwards direction. That would mean that on the coming from the left side, if it's opposing, if it's opposite, then I have to be going up. So those are the two things that can occur when you have an odd multiplicity on your vertical asymptote. Okay, so I think we have everything we need now to do our graphing. So you have to be really careful when you're graphing rational functions. So we're gonna be careful. I'm going to take it kind of step by step for our graphing. There's a lot involved. So we're just going to do generic graphing, nothing super detailed. We just want the general picture. So the whole point of this is not to use a calculator to graph or a computer to graph, but we want to use our analysis carefully, very carefully, to get a good general picture of the graph. It doesn't have to be super accurate though. Okay, so we have a rational function here. Okay, I should say exercises. Get rid of this here. Exercises. graph the rational function. Okay, graph the rational function. I'm going to include vertical asymptotes, horizontal asymptote, the x-intercepts, the y-intercept, and I might include one extra point sometimes, a test point to help me get this thing graphed. All right, so I'm going to begin with, first of all, the vertical asymptotes. So remember to find the vertical asymptotes. You're going to look at your denominators. And if it's factored, hey, things are already factored. Now, sometimes you have to factor, but this one's already factored. You take your denominators and you set them equal to 0. So we're going to have, let's see, x plus 4 equals 0. When I solve for x, I'm going to subtract 4 from both sides. I'm going to get x equals minus 4. That has an odd multiplicity, right? An odd multiplicity. Why is it an odd multiplicity? Because the multiplicity is 1. Right? Multiplicity is 1. That's basically the power above x plus 4. You can imagine there being a power of 1. Okay. Also, I'm going to do x minus 1. That's my other factor here in the denominator. I'm going to set that equal to 0. That's going to give me that x equals, add 1 to both sides, x equals 1 has, this one has odd multiplicity 1 as well. Why odd multiplicity 1? We'll look at the power here above x minus 1. It's a power of 1. Okay, so I want to do my horizontal asymptote. So to do that, we're going to look at the degree of the top and the degree of the bottom and compare the degrees. So what is the degree of the top? I'm going to call it the top when f of x. The top has degree 1, right? It's the largest power on top is 1. And what's the degree of the bottom? Well, the bottom has a power of 1 and a power of 1. You can add those powers together. So add the multiplicities together. 1 plus 1 is 2. That's going to be the degree of the bottom. The degree of g of x, I'm going to call it equals 2. So the top has a smaller degree, right? The top is degree 1. Bottom is degree 2. So since the top has a smaller degree than the bottom, then there's a horizontal asymptote at y equals 0. Okay, what else do we do here? I think we're going to find our x-intercepts. So x-intercepts, you just take the top, set it equal to 0. So I'm going to subtract 2 from both sides. I'm going to get negative 2. And we want to think about the multiplicity. Is it even or odd? Has odd, right? The power up there, if you imagine there being an x plus 2 with an exponent, it's x plus 2 to the first power, has odd multiplicity 1. And finally, I am going to look into my y-intercept. So to find the y-intercept, we're going to plug in basically 0 for x. So I'm going to do blank plus 2 over blank plus 4 times blank minus 1. So everywhere I have an x, I'm plugging in 0. So on top, that's going to give me 2 over 4 times negative 1, which is 2 over negative 4. That reduces to minus 1/2. Okay, so I'm going to take everything I have here. I'm going to start my graphing. Where am I going to do my graph? I'll do my graphing here. Okay, I'll try to keep things a little on the straighter side. It helps to be organized. This is my x-axis, this is my y-axis. So I'm going to begin by putting down my vertical asymptotes. I have a vertical asymptote at -4 and at +1. So here we're going to have 1, 2, 3, 4. And 1 at +1. So these are vertical lines that the graph will never cross. The graphs will approach them. We have a horizontal asymptote at y = 0, so that's going to be y = 0 is this line right here, the x-axis, right? We have an x-intercept at x = -2, so -2. Now I'm going to use red to do my graphing here. That's right there, right? So we have an x-intercept right there, so I'm going to plot that. And we have a y-intercept at -1/2. So let's say this is -1 on the y-axis, so -1/2 would be right here. Okay, now what I want to do, I want to start on the right side. Generally, you want to start on the right side of your rational function. So the way rational functions look, they follow the asymptotes very carefully. So notice we have on the right side, we have this vertical asymptote here at 1, and we have this horizontal asymptote at y = 0 here along the x-axis. So your graph's going to be somewhere either up in this corner, and it's going to follow the vertical asymptote and the horizontal asymptote, or it's going to be down in this corner like that. So it's going to follow the x-axis and the vertical asymptote. So that's the way it behaves. So you have basically two options, this one or this one. So how are we going to figure out which one it is? Well, there are ways to do that, but I'm going to give you a technique where you take a test point. So we're going to take a test point. What color will I use for my test point? So your really important numbers along the x-axis are -4, right? That's that vertical asymptote. -2, that's that x-intercept. 0 along the x-axis gave you your y-intercept. +1 was another vertical asymptote. So what we're going to do, we're going to take a number to the right of our right most important place. So our right most important place is here, this vertical asymptote at 1 right here. So let's pick a number here along the x-axis, just to the right of that. Let's pick 2 right here. I'm going to pick 2. So I'm taking something to the right of the right most important x value. So the right most important x value was 1 here, right? That was our vertical asymptote there. So I'm going to pick 2, and I'm going to do a test point with that. Let's use purple. So I'm going to use a test point at purple. So taking a test point, So I'm going to pick x to be 2, and I want to see what my y value is. So I'm going to take 2 and plug it into my function. So I'm going to, on top, I'm going to have 2 plus 2. And on bottom, I'm going to have 2 plus 4 times 2 minus 1. Let me actually plug in the 2, right? So 2 plus 2, 2 plus 4, 2 minus 1. So we plugged in 2 for all the x's. Now let's calculate this. So on top, I'm going to have 4, and on bottom, I'm going to have, let's see, 8 times 1. So that's going to give me my y value to be 4/8, or simply 1/2. So when my x value is 2, my y value is 1/2. So let's plot that point. So 2, comma 1/2. Well, let's say this is 1 on the y-axis. So 2, comma 1/2 would be about right here. And there's my test point. That's to the right of that vertical asymptote point. Okay, so I'll make that actually red. So now we know that the graph of our rational function begins on the right side in this upper corner. So it's going to follow here the y-axis upwards, and it's going to follow on the right side. It's going to follow this horizontal asymptote. Now we know it never goes below the x-axis on the right here because there's no x-intercept, right? There's no x-intercept to the right there. We know there's only one x-intercept in this whole entire graph, and it's over here at -2. At -2. So it's never going to touch the x-axis as you go to the right. Now, so we got the upper right side finished. Now we're going to go just to the left of the vertical asymptote at 1. So what do we know about the multiplicity of the vertical asymptote at 1? Well, at 1, the vertical asymptote has an odd multiplicity, right? Odd multiplicity. What does it mean when you have an odd multiplicity about a vertical asymptote? That means that the graph will go in the opposite direction about the vertical asymptote. So on the right side, the graph goes up towards the vertical asymptote. That means on the left side of 1, so here's 1 right here. 1, oops, I lost it. Here's 1 as a vertical asymptote. On the left side of 1, your graph is going to be doing the opposite of what it was doing on the right side. So it's going to be going down in this direction. Down. Now that graph, which is going down towards the vertical asymptote, has to connect to this y-intercept. So it connects there. And then this y-intercept, we know, has to connect to this x-intercept of -2, which we had plotted. Now what happens at the x-intercept of -2? Well, let's pay attention. The x-intercept of -2 has an odd multiplicity. What does that mean? That means our graph is going to cross. Not kiss it, but cross. So we're going to cross. We're going to go across here. At -2, we're not going to kiss it. Now, is it possible for our graph to go back down this way towards the vertical asymptote at -4? Is it allowed to go down there? No. It can't go down there. If it tried to go down there, it would have to cross the x-axis, and there would be another x-intercept, but there's not. So our graph can't go down. Our graph is forced to go up this way towards the vertical asymptote. It's forced to. It cannot go back down because it would have to cross the x-axis and force another x-intercept, which we don't have. Okay, so I know the graph crosses the x-axis at -2, and then it has to go up towards the vertical asymptote. Now, what's it doing on the other side of the vertical asymptote? Basically, there are two things. It could be either going up towards the vertical asymptote at -4, or on the other side, it could be going down towards the vertical asymptote at -4. We have to figure out which is it doing. So we're going to pay attention to the multiplicity of the vertical asymptote -4. So here's -4, right? -4 was a vertical asymptote, but it has an odd multiplicity, right? Odd multiplicity. So odd multiplicities mean you're going to have opposite behavior about vertical asymptotes. So notice on the right side of -4, the graph is going up. So that means on the left side of -4, our graph has to be heading down. So our graph has to be heading down this way, opposing about -4. So it heads down, and then our graph has to come up here as it goes left, and it has to approach the horizontal asymptote. It's not allowed to cross the horizontal asymptote because there's no other x-intercept there on the left. No other x-intercept, so it's not going to cross the x-axis. Now, there you have it. This is your function. I'll call it R. It's the graph of R. Yeah, so you have to keep in mind that rational functions, when you graph them, they follow asymptotes. they follow asymptotes. They will never cross vertical asymptotes. They will never cross vertical asymptotes. Sometimes they will cross horizontal asymptotes, as we can see right here, right in the middle. We crossed -2. -2. We crossed at -2, right? We crossed the x value at -2. Even though there was a horizontal asymptote along the x-axis. Okay? So that's a good introduction